This is Bob McFetrich with Beckwith Electric. I'd like to thank you for downloading our M-6200 training. This particular session will be on line drop compensation, and it'll have two parts. Part one will be the basic settings, which are RX and Z. In part two, we will be discussing other compensation methods such as VAR biasing and remote voltage biasing. And again, we are focusing in on the M-6200A single-phase regulator control, but most of what's being covered in this presentation is also applicable to the M-2001 Series B, C, and D. So, line drop compensation is used to compensate for a voltage drop. So, we know that we have regulating devices inside the fence, whether it's an LTC, bus regulators, or feeder regulators. And we realize that inside the fence is where the voltage is the best and where we probably need them the least. We know that voltage is going to drop as we go down each circuit due to the impedance of the circuit and the loads and the current being drawn by those loads. As the current flows through the impedance to get to the loads, it causes heating and therefore a voltage drop. So we know that the voltage will drop as we go further down the line, and we need to have some means of correcting it. And since we put the regulators instead of further down the line, we put them at the source. What line drop does is it tries to anticipate what the voltage is further down the circuit and regulate to that voltage as opposed to the voltage it's measuring at its particular location. We also want to keep in mind that reactive current is going to cause 3 to 4 times more voltage drop than real current because the reactive impedance is greater than the real impedance. So, with line drop, we have to have two portions. We have to compensate for the real and the reactive portions of the line drop. So, we have two different settings with the traditional R and X, where the R setting is going to be the real portion and the X is going to be the reactive portion. And the settings will be entered in as voltages, and the voltage that's entered is the voltage at full scale. So full scale current is 200 milliamps, and I have a positive 5 for an R. That means if I have 200 milliamps of real current, apply 5 volts. If I have 100 milliamps of real current, apply half of that, which would be 2.5 volts. So it's a linear approach, and it's calculated using the system impedance. So we're going to try to determine what the voltage drop, anticipated voltage drop is by calculating the system impedance. And that impedance is the impedance from the load side of the regulator to whatever we're going to define as the load center or the point we're trying to regulate. So it may not be the entire line. It may only be a portion of the line. So, for instance, in this example, if we assume that the load center is here, then the impedance we're looking at for our calculation is this impedance. If we assume that the impedance is here, the load center is here, this is the point we want to regulate. So our regulators are on the bus, but we really want not this voltage to be 120, but we really want the voltage at this point to be 120. So the impedance we're going to use is going to be this impedance here, from the load side of the regulator to the load center. We're not concerned with this impedance here past our load center. So if we look at it and we say that there's a 5 volt drop at full load, what we're saying is if I were to regulate at 125 here, that should keep us at 120 there, and therefore if we were to assume that this impedance was all resistive, we would need an R of 5. Now in actuality, this impedance will be a combination of both, and therefore we will have both an R and an X. And when we have a combination of both, let's say we had a setting of 4 for R and 3 for X, it will apply 4 volts to the real portion of the total current and it'll apply 3 volts to the reactive portion of the current, and then it'll add those up, and that'll be the total voltage that is applied. So the formula to calculate the line drop is we're going to look at the impedance of the circuit between our regulator or LTC load side and the load center, wherever we want that to be. And the formula is, the setting is going to be calculated by the CT, the full load current, divided by the PT ratio times the real portion of the resistance. And the X setting will be the same thing, only using the reactive portion of the setting. And again, the R and the X impedances that we're going to calculate are not of the entire line, but only the section between the regulator and the load center that we are selecting. If I were to select my load center to be at the end of the line, then it would be the total impedance. But if it's not, if it's before the end of the line, then it's to the point of the load center. So let's look at a couple graphs of what that really means. So here we have a case where we have our full load current, percentage of full load current, and this would be the R or the X setting. So for instance, if I were to set a value of 10 for R, we would see that at 100% rated current or full load, we would apply 10 volts. So we would add 10 volts to our band center. At half load, you can see that we're only going to apply 5 volts. But notice as the load continues to increase, we're going to continue to add more bias. So at 150%, we're actually going to add 15 volts. And if we were to allow 200% of load current on that regulator, we would actually add 20 volts. If we had a setting of 5, it would be similar. At 100%, we're adding 5. At 200%, we're going to be at 10 volts. So there is no cap on traditional line drop settings, R and X. So we have to keep that in mind, or if we have more current than we anticipate, we could have an overvoltage situation. For an R, so we're going to put in a positive 5 for an R. So 100% in the forward direction, we're going to add 5 volts. So if our voltage is 120, we're going to add 5 and we're going to make it 125. But notice that if we go reverse power and we have current flowing in the negative or the reverse direction, we are actually going to be lowering the voltage by 5 volts at full load current in the reverse direction. So in the forward direction, a positive R or positive X will bias the regulator to want to raise the voltage more. But in the reverse mode, a positive R or positive X will encourage it to lower the voltage. So if we want the regulator to always be raising the voltage at the point where it's at, we would want a positive value in the forward direction and a negative value in the reverse direction. Now, if reverse power is due to sectionalizing and we have regulate in reverse selected or regulate in reverse measured, then we don't have to flip the sign because it knows the source has changed. So the current really is still in forward direction, just from a different source. So we would consider that a reverse power and that it's reversed from its normal source, but the current flow direction we would still consider forward because it is going from its new source towards the load and not from the load towards its new source. But if we're in reverse power due to the DG, for instance, distributed generation, in that case our source is still our source, and now we actually have current flowing from load to source instead of source to load, and that's when we would have to flip the sign. So we're going to cover reverse power in a different session, and you can reference that session also. But the general rule of thumb is if you're selecting ignore or DG mode, then in those two modes we're saying the source is still the source, and if we see current come in reverse, it's because it's coming from the load into the source as opposed from the source to the load. And in that case we would want to flip the signs in forward and reverse settings. If it's due to regulate in reverse or regulate in reverse measured, then we would not need to flip the signs, because we are saying that the source is now changed in reverse power mode and that the current is still flowing in the direction from the new source to the load. So we must keep this in mind, that depending on which way we're regulating in reverse Y, whether it's DG or sectionalizing, we may have to flip the sign. If we do not, and we're in DG mode and we have a positive 5, when the generator is offline and we're going in forward direction, we will be adding 5 volts and trying, so the 120 band, we'd actually be using 125. But if the DG was fully online, we would actually be subtracting, and we would actually be lowering the voltage at the substation bus, which would not be a desirable thing and would typically cause low voltage. And we're going to be covering that more in detail in the next session on line drop compensation. But here would be our typical settings in the control. So we have 2 methods. We're currently talking about RX. There's a second method we'll be covering a little later in this session for Z. But if we select RX, you can see that we can put a value either positive or negative for both the R and the X in the forward, and depending on the power direction, we may also be able to put a value in the reverse direction. And this is where you may want to either flip the sign or not flip the sign. So how does one go about calculating the proper RX? Well, the first thing we have to do is we have to determine where our load center is going to be on the circuit. And the load center is basically where we think the majority of the midpoint of the load is. So where do we think half the load is? In a typical circuit, 3/4 of the load will go over the first half of the circuit. Knowing that the load center is typically somewhere between 30 and 50% of the length of the circuit. Once we determine that, then we're going to calculate the impedance to that position. So some utilities will use the 3/8 rule, where since half the current is in the first, 3/4 of the current is in the first half of the circuit, to find the midpoint of that, we would take 1/2 times 3/4, and it would be 3/8. So 3/8 of the way down the circuit would be where we would determine our load point to be, and that's where we would calculate the impedance to that point. So how does one calculate the impedance? Well, the impedance of the circuit is first determined by the spacing of the conductors. And so we have an equation here that will calculate a value depending on the different spacings. So we're going to take the spacings of all 3, multiply them, then take the cubed root of that, and the result will give us the average spacing. So we're going to look here, we've got a spacing between this conductor and that one, between these 2, and between those. Whatever those dimensions are, we're going to multiply them all together, take the cubed root of that, and then the result will be our average spacing. Once we have that, the next thing we have to do is determine the material and size of the conductor, because each conductor has a different impedance value, and it's given per mile. So this impedance value is per mile. So we'll have to go to a lookup table and determine what our impedances are. So for instance, for a 266 MCM, the resistance would be 0.385, and the reactance is going to be depending on the diameter of the cable. In this case, if we have a 36-inch, which was the spacing, what we just calculated, so for a 36-inch, we're going to be using 0.598 for the X value of the impedance. Once we have the impedance per mile, then we have to calculate from that what the total impedance is by the length of the circuit. So again, these impedances are in ohms per conductor mile, and therefore we must, and it's also assumed it's for 3-phase. If we were hooking up delta regulators, we would also have to multiply by 1.73, or if we were doing a single phase tap and this was for a single phase regulator only for 1 phase, then we would have to multiply by 2. So once we've determined that, we multiply our values by the total distance. In this case, if we assume 1.1 miles, Then we will multiply these two by 1.1 and come up with our new values for our impedance. Once we have the impedance, we have to nominalize or get into per unit quantities. And to do that, we have to have a base. So in this example, we're going to assume that the base voltage is 13.8 and that the current is going to be 600 amps. And from that, we can calculate a base impedance. And the base impedance would come up to be these two numbers here. So we're just calculating our real portion and our reactive portion. So once we get the base at 13.3 ohms, we know what our real portion was from the previous slide. Divide that by 13.3, and that per unit's that. And the same with the X from the previous side. We per unit that. Now we have our per units, but it is on a 120. These are going to be voltages, and it's on a 120 base. So all we have to do now is multiply them out by 120, round them up, and that gives us our R and our X values. So for this particular example, we would want an R of 4 and an X of 6. So our desired voltage was 120 at full load current, 600 amps. Now, there are two factors that play with the line drop, and that is the amount of current and the power factor. So what we're going to do here is we're going to show you how, when the power factor varies, it can vary the amount of R and X. And the reason is because as the power factor gets to unity, we have all R and no X. As we get further from unity, the amount of R being applied will be less, and the amount of X being applied will be more. So if we were to do the calculations, we could see, for instance, a 0.8 power factor, we would have to have the bus voltage at 126.82 to keep the desired voltage at the load center at 120. But over here, if we do the math at different power factors, you can see that as we go further away from unity, we have to raise the voltage higher to keep that voltage downline the same. And again, that's because there's more voltage drop due to reactive current than real current. So the more reactive current flowing through the circuit, the more voltage drop we have. And therefore, the higher we're going to have to raise the voltage. Likewise, the same condition with the current. As the current goes up, we have to raise the voltage more. So at half full load, we would only have to be at 123.4 volts, but if we went to 1.5 times full load, we could be at 130.25 volts. So this shows you the need to supervise your line drop compensation. If the power factor gets too far away from unity, or if the load continues to increase, either of those conditions is going to cause the voltage at the bus to keep going higher to keep that downline voltage stable. So we will need some type of supervision to cap the voltage from getting too high. And that is covered again in a different session called blocking, but we're going to cover it quickly here. And the two things we're going to have are our block raise and our deadband. Basically, the block raise says that if the measured voltage, not the compensated voltage, but the actual measured low voltage before we apply any compensation, if that voltage gets above 128, we're going to cease to raise the voltage any higher. But even if we stop raising it, it can continue to creep up as load starts to go away, or maybe a cap bank closed, or maybe the high side voltage has been raised due to a high side capacitor closing. And if the voltage gets to above 130, which would be the block raise added to the deadband, then that will actually force a lower to bring the voltage back down, and that's referred to as the first house protection. So remember, the voltage is always going to be highest for the customer closest to the source, and therefore, if we apply too much compensation, we may risk over-voltaging that customer in an attempt to keep the customer at the end of the circuit at a high enough voltage. Now, capacitor banks, switch capacitor banks will have an effect on the line drop compensation. As we said earlier, there is more voltage drop due to reactive current than due to real current. And with capacitors, they are going to provide that reactive current to the load. So, any capacitor that is on the load side of the regulator will impact it, and we need to account for that. And it impacts it in two ways. First of all, it is supplying reactive current, and that reactive current has to go from the cap bank to the load through the line, and therefore that will cause some drop. But at the same time, when the capacitor is closed providing that current, it's also providing a voltage lift downstream. So we've got the combination on one end, the cap bank is going to cause additional voltage drop as that reactive current is going through the line to get to the reactive load. But in the other end, it's also going to create a voltage rise. So will the two offset each other, or will one of the two play a bigger role than the other? And that depends on where the cap bank is placed. For instance, in this case, if the cap bank is placed right below the load side of the regulator, and the load is down at the end of the line, then when that capacitor bank closes, all the reactive current has to flow the whole way down the line to get to the load. And therefore, we're going to have maximum voltage drop. Because the capacitor is close to the source, it will have very little effect on the voltage. The effect the capacitor bank has on the voltage is a combination of the size of the bank and the distance or the impedance back, the fault impedance back to the source. So at very close range, you have no impedance, and therefore you have no voltage change. So in this case, what can happen is when this bank closes, we're not creating any voltage rise due to the capacitor bank, but we are creating a larger drop due to all the reactive current going this way to the load. And the regulator does not see that reactive current because its CT is upstream of it. So the regulator doesn't see that all this VAR current is flowing, so it's not attempting to compensate for it, and the capacitor bank is not providing enough lift in the voltage, and therefore we could risk having under voltage at these customers near the end of the circuit, as we are undercompensating on the X side because we don't realize that capacitive current is flowing through the system. Now, if the capacitor is at the midpoint, we kind of have the combined effect in that now the reactive current, if the load is still at the end, it still has to flow down, but it only has to flow down half the impedance, so it's only creating half of the voltage drop it would have in the first example. Also, because we're further away from the source, now when this bank operates, we will have a voltage rise, and that voltage rise may be significant enough to offset the difference in the loss of voltage due to the reactive current, and here at the end of the line the voltage may be fine because we're getting a reduction here that we did not anticipate here, but we're also getting a rise here, and if the amount of rise is equivalent to the amount of drop due to the reactive current, it's a wash, and the voltage at the end of the line will probably be okay. Now in our last example, what if the capacitor bank is right at the load? Well, in this case, if we're right at the load, the current does not have to flow through any of the line or very little of the line, and therefore it's creating very little voltage drop. But the capacitor being closed at the end of the line is having the maximum benefit in raising the voltage. So in this case, we're going to have our largest delta V. We're not going to have any reactive current loss to compensate. And if anything, we'll have a higher voltage here than back at the bus, which should not be an issue. So those are the effects that a capacitor bank, a switch bank, can have on a LTC or a regulator. Anything to the load side of that, the regulator or LTC cannot see that reactive current, and therefore if the capacitor bank is supplying reactive current, the regulator does not know that that reactive current is there, and therefore is not attempting to compensate for the voltage drop that is being caused due to the reactive current. But that reactive current voltage drop may be offset by the voltage rise given by the capacitor bank, depending on its proximity to the source. So, as a general rule of thumb, it can be difficult to coordinate the X setting if you have switched capacitor banks, and many customers will actually use an R only and not even use an X setting. If you are going to use an X setting, it will work best when your banks are close to the load so that we are not causing any further reduction of voltage due to line drop. Likewise, we'd like the capacitor banks not to be right next to the source. Now, line drop compensation RX works great for feeder regulation or line regulation where you only have one impedance. But what if we have bus regulators or an LTC? In this example, we have either a bus regulator or an LTC. We have 4 different feeder breakers. So each of these feeders is going to have different loading and different impedances, and therefore if we were to calculate, they would have different load centers, and we would be calculating different RX values for each circuit. The problem is the regulating device is regulating all circuits simultaneously, so what do we do? Well, one approach would be the Z method. In the Z method, what we are going to do is at full load, we're going to measure or calculate what the voltage drop is going to be across each circuit. So in this case, let's assume the voltage drop in this circuit is 2 volts, this one 3, this one 4, and this one 6. We would take the largest of those, which would be this one here at 6, and that is the value we would enter in. So it's only one value. We would enter it in, and what that'll do is at full load, it will apply 6 volts of compensation. And it'll be linear, so at half load it would be applying 3 volts. And so it's trying to average everything out. And it's using the magnitude of the current only. It's not doing a phasor on the current. So if we were going to use the Z approach, we would select Z here instead of RX, and then notice now the RX settings are grayed out and we only have one setting, which is for Z, and we only have one value for Z. And that value, notice, can only be positive, it cannot be negative. So again, as an example how to calculate Z, whatever the voltage drop was, whatever the load conditions were when we calculated or measured the voltage drops, we'll use that as a scaling factor to create our base. So for instance, if the load is only 150 milliamps and the maximum voltage drop measured at 150 was 5 volts, then what we would do is, we know our full scale is 200, so we would have to take the 200 divided by the 150, multiply that by the 5 volts, and we would actually enter in a value of 6.7 volts. Now, also remember that Z has the same dynamics as RX, and that is the load increases, the compensation will continue to increase, and therefore we still need to have that supervision. We're not worried about the power factor, which we were in RX, but we still are worried about the total load. So Z is not looking at the phasor, it's just looking at the total current. So we don't have to worry about the power factor getting further from unity, causing the bus voltage to continue to increase. But we do have to worry about if the load continues to increase. So in summary, the Z approach is best used for LTCs or bus regulators, where you have one device regulating multiple circuits that are not close. Now, if the circuits get too far apart, we need to handle that too. So for instance, if I were using Z and I had 4 circuits, and in the previous example, they were 2, 3, 4, and 6. There was only a 4 volt delta between the low and the high. If I have more than a 6 volt delta, let's say it's 2, 3, 4, and instead of 6, let's say it's 8. I would probably not want to use Z unless I put a line regulator on the 8 at the midpoint. Then I can change that 8 to a 4 because we would only be regulating the portion of the circuit up to the midpoint regulator. So when using Z, we'd like to see the discrepancy between the different circuits to be no larger than between 4 and 6 volts. And if the discrepancy gets larger than that, then we need to look at either putting in some capacitor banks or some line regulators to try to keep that voltage drop between all the circuits between 2 and 4 volts. So that is the basics on line drop compensation. I hope you've now get a better appreciation as to why it may be needed, how you would calculate it, why you would use RX or Z, how capacitor banks may affect it, and how we have to supervise it as the load increases. So in session 2 of this particular session, part 2, we're going to talk about some enhanced features including capped compensation, VAR biasing, and remote voltage bias. If you have any questions, comments, or concerns, you can submit them via the same web portal. And as always, we thank you for your time and interest in Beckwith products, and we hope you have a blessed day. Bye-bye.